It seems inconceivable that human beings could ever be reduced to a mathematical model like starlings. But Ian Cousin studies how animals behave in groups, and his research has revealed some surprising parallels.
How can you possibly begin to understand something like this huge mass of people? Even when you look at the crowd for a few seconds, you realise there's so many complicated factors at play.
Well, I started my research looking at simple organisms like ant swarms, schooling fish, and remarkably, our insights from studying those systems led to new insights in studying human crowds.
But people are much more complicated than a fish or an ant.
Exactly, but that's almost the beauty of this, is we're thinking about much more interesting things when we're walking through crowds than how do I avoid that person, how do I avoid that obstacle. You know, we're thinking about what we're going to cook for dinner or what our friends are doing. And so, in actual fact, we're almost in autopilot. And we're actually using very simple rules of interaction, just like the schooling fish and the swarming ants.
So can we learn things from the ants?
We could learn an immense amount from the ants. The ants don't suffer from problems such as congestion because they're not selfish, and I'm afraid to say we are. We want to minimize our own travel time, but we don't necessarily care whether we do so at the expense of other individuals.
Of all the animals Ian has studied, human beings are, in some ways, the most predictable. We walk at an optimum speed of 1.3 metres per second and prefer to walk in straight lines to get to our destination.
What happens is you will naturally fall into the slipstream of an individual moving in the same direction as you. And so without you even knowing it, you're forming a lane. And similarly, pedestrians moving in the other direction will also form lanes, very much like the ants do.
These lanes help us to avoid collisions. However, in a large open space, like the concourse at Grand Central Station, the lanes inevitably cross each other, which could lead to congestion. But if you put an obstacle, like this information desk, in the middle of the crowd, rather than getting in the way, it acts like a roundabout and increases the flow through the station by as much as 13%. These rules are so effective at predicting what we'll do. They can even be used to simulate crowds of people.
Each individual is actually described by a set of numbers as they move through an environment.
Exactly, we're capturing the average type of behaviour of pedestrians. We're capturing these simple and local rules that people use within crowds to then make predictions as to how the whole crowd is going to flow through different types of environments.
We can use this underlying code of the crowd to design buildings that are more efficient and safer.